Welcome to lecture 2 of Unit 4. Just to remind everyone before we get cracking, you've just done your big homework, as you probably remember, and you have a quiz tomorrow. So I won't be lecturing you tomorrow. Yoni will organise the quiz. I'm not sure. I'm sure that's all organised, but I don't have anything to do with that. And today we'll go 2 hours, continuing through basically like the foundations of how to use Julia, like you know how to build your programs and data structures and things in Julia, and we'll continue for that next week on Monday. Okay, so I'll be back next Monday, but only for half the time. So we'll switch over then to Paul Verbeek. Is that correct? It says Yoni, or maybe we switch to Yoni. But basically leading into Unit 5, which is about computer algebra systems and things like that, which is pretty fascinating. Are there any questions about the sort of course structure before we get back to the content? No? All right. Cool. All right. So I'll just recap what we did on Tuesday. So Tuesday, I just gave a little bit of a motivation for why we might be interested in Julia, why we want to learn about it, like what we want to get out of Unit 4 is just so that you can feel more comfortable writing larger pieces of software in Julia, so that you can smash out projects 1, 2, and 3 without sort of being handicapped by confused about the syntax or the functions or something like that, right? So, and hopefully I'll instill a few good habits on how to like design a program so that's sort of easy to understand and maintain and stuff going forward. Right, so Julia is a language which sort of tries to be fast and let you code fast and let you code programs which sort of can be reused and be, you know, shared in a team environment and things like that. Sort of just went through the syntax, the kind of expressions that you see in Julia. I mentioned this idea of syntax sugar. So even an expression like this in Julia, remember, is syntax sugar. So in Julia, you know, 1 plus 3 is the same as plus 1, 3, right? And so that kind of trivial transformation of how you write things is something we often call syntax sugar. There's all different sorts of syntax sugar, like these question marks for if statements and things like that. We spoke about blocks of code, how in a block, the last thing in the block is that sort of the value that a block of code has. Spoke a little bit about nesting scopes and things, macros, and the sort of the syntax for functions. Okay, like how remember in functions there's all these different ways of writing the same thing. There's a function form like this, a long form, a short form, sort of an arrow function or anonymous function kind of form, and you can even make the other types of function forms anonymous by just not writing the name. We spoke about closures, which are kind of like data and functions all put together, smushed together. So if you've ever heard of or used an object-oriented language, like the classes and the objects in an object-oriented language, also sort of data and function methods sort of put together in the one data structure. And there's actually kind of like a mapping. If you have a language with closures, you can actually build an object-oriented system. Or if you have an object-oriented system, it's sort of enough that you could build up closures, so to speak, sort of manually, like I showed down here below, sort of like this kind of pattern. We talk about how we write types and type assertions in Julia, and we're going to talk a lot about types today. Functions with argument types and functions with different, you know, adding methods to functions. Varargs function, so this ... sort of indicates there might be multiple things there, right? And that's where we got up to. So we had this sort of example where we could make a polynomial, import this sort of roots package and do that. So I believe this is where we're up to, somewhere about here. Okay, so what I'm going to do is I'm just going to go through some remaining bits of syntax. Then I'm going to go into types. You'll learn sort of how types are even sort of implemented inside Julia and how to think about them. And then we'll probably have a break, come back and talk about the functions, methods, multiple dispatch, how to use multiple dispatch, how to use an interface, how to create type hierarchies and things. So we should have a good amount of content here, and we'll see where we get to at the end of these 2 lectures, these 2 hours, and we'll have some more content next week on program design and things like this, modules. All right, so a function can have an arbitrary number of arguments with the ... thing like this, right? But you can also say create a function where you have, that there's sort of 3 parameters, but sometimes it's sort of, there's some sort of default value for some of these. Like you might have a Gaussian distribution, and like by default, you might care about like a normal distribution where the standard deviation is 1 and the mean is 0, right? That's just a normal distribution, but you might want a more fancy one where, you offset the distribution by the mean, or you scale a distribution by the standard deviation. So you can sort of see here that we offset the offsets and the sort of scales and things coming into this. Oh wow, computer's slow. So PDF. Oh, right, sure. So this is just sort of proving that they're using the distributions package. The probability density function for its normal function is matching the same as our one. Okay. Yeah. At the value x equals 1.5. All right. Wow, this computer is really lagging. Sorry about that. In Julia, you have positional arguments that we've already seen. But if we want, we can make the arguments have a name. So rather than try and remember my function has like 10 inputs and like which ones, it's easy if it has 10 inputs to mix up the 7th and 8th one and get them in the wrong order, for example, because it's just hard to keep in your head. It's not so bad for like a plus b, like functions with 1 or 2 arguments, but when you get a lot of arguments, it gets tricky. So you might want to like give them names or keywords. And the way you do that in Julia is when you define the function, you use this semicolon. So the only difference between this function and the one we had earlier is this was a comma earlier, and now it's a semicolon, okay? So this is one of those things where syntax is interesting, right? Like it's a very minor syntactical thing you can look over, but it makes a big difference to how you use the function. Again, with a keyword argument, you can define a default value. You could also not define a default value. So it's sort of, it's not optional. You have to, it's mandatory to specify it, but it has a name. It's not just like argument 1, argument 2. It's like mu equals 0 or sigma equals 1, that kind of thing. And so when you call it, you could either, so this is an interesting thing as well, you could either use a semicolon or a comma here to separate the positional arguments and the keyword arguments. Okay, so you'll see both depending, but generally once you switch over to something equals whatever, Julia will just think, okay, he's trying to do a keyword argument. You're trying to do a keyword argument, so we'll interpret it that way. And again, you can use this sort of ... to kind of slurp and splat the arguments to a function. And so here's a very flexible function that takes an arbitrary number of arguments, an arbitrary number of keywords. It doesn't really care what they are. And it'll just slap them all up and put them in data structures, so like tuples and name tuples and things. So if you have a look at this function call, we've called it with 2 unnamed arguments and 3 ones with names, okay? And so the standard arguments is just this tuple. The positional arguments are just this tuple, 2.5 and false, the first 2. And then the keywords are this data structure. Now, basically, it's this thing called a name tuple, but it's this view of a name tuple, the pairs of it, which means if you iterate them, you get both the keyword and the value, not just the keyword. No, not just the value, sorry. So that's a whole lot of output here, but really it's just meaning sort of those last 3 lines. Okay. All right. We'll just keep going through a bit more sort of syntax. Earlier, I did show you there's like 4 different ways to write functions, there's sort of like a fifth one because 4 wasn't enough. So there's this thing called do syntax, which creates functions, creates closures. Okay. So as you can know, you can kind of create functions as arguments. You might want to create a function, pass it into another function, and have it evaluate it. A good example of this is filter. Okay. So in filter, you get to provide like a user-defined predicate. A predicate's a function which returns a Boolean number, true or false. Predicates are. So you get to define some sort of predicate function. In this case, it's this little arrow function here. Okay. So what this means is if x is divisible by 10, it returns true. And if x isn't divisible by 10, it returns false. Okay. And what filter will do is it will only keep elements where the predicate's true. Okay. So here we've got an array with this rand functions create an array with 100 things, and the elements are randomly chosen between plus and minus 10,000. Okay. It's just some data we made up, right? And so if we filter on that, we get these things. And you notice they all end in the number 0, right? Because they're all divisible by 10. Everything that wasn't divisible by 10 got thrown in the bin. This hasn't actually edited data, right? It's returned a brand new array. It's like created a new bit of memory and put in the new things in there. Okay. In Julia, see this exclamation point? If I had to use the function there with an exclamation mark, it would have edited data in place and mutated it. Right? And we'll talk about mutation a bit later. All right. So, but what if that predicate function, that anonymous function you provided, had more lines of code? It was more complicated. You couldn't just stick it in a little block of code like this. For example, we want to deal with prime numbers, but we kind of want to deal with maybe this is contrived, but like if it's a negative number, we want to like check if it's the negative of a prime number, for example. And so we could write a multi-line function here, and it doesn't need a name, so we've left it anonymous, but it's still a multi-line function that starts and ends here. Now, without sort of dragging my mouse and making that blue, right, I find it personally a little bit difficult to sort of look at that and kind of know where the function starts and ends. I might forget that this data here is actually an argument to this function there. They're kind of visually quite separated, right? So visually, this isn't very, it has a few detractors. It's not. It could be made a bit better, and that's sort of the purpose of this do. Okay. So what the do syntax does, it's syntax sugar, so it's a little magic. It creates a function, like an arrow function, like an anonymous function, and it automatically sticks it into the first argument here. Right. So by convention, all these Julia functions like filter, map, reduce, open, there's a bunch of functions, and the first argument is expected to be some function you provide, right? And so, and from here onwards is a sort of normal standard anonymous function, but it says do here instead of function, right? So it's a bit funny, but I just wanted to show you this because you do see this from time to time, and when you haven't seen it before, it's like, what on earth is that doing? Okay, but it is sort of convenient because you can kind of like create sort of code in place in a little bit more friendly way than you would have otherwise. Okay, but again, it's just a minor piece of syntax sugar. All right, more syntax sugar. Destructuring. So when you create some data, it's called constructing it, right? So we can take two things and create a tuple. So this thing in brackets here is a tuple. It's a data type. We'll talk about them a bit later. But you can also undo that. So that's constructing it. You can also destruct it by like having a tuple on the left, and it'll bind A and B to the values in those slots. Okay. And so you can see A becomes 42 and B becomes ABC. Yeah. A trick you often see in Julia is you use this syntax, oops, again with the slow computer. Don't know why. Maybe Zoom is too much for this computer because it was fine before. You can see here this little line of code. So this is a cute little trick for swapping variables, right? So with programming languages, what you'd normally do to swap variables is like create a temporary variable, So temporary hold, say the value of X, and then update Y to the value, X to the value of Y, and then update Y to the value of the temporary variable, right? And it's like requires 3 lines of code. Whereas you got this cute little trick and you can just sort of swap them like that. Okay. A nice thing about Julia is it actually understands tuples very, very well, the compiler. So that will actually optimize to beautiful code. So you don't have to worry about it being slow or something weird like that. Okay. Similarly, you can destructure like a name tuple, or like the keyword arguments. You can destructure things according to their name, not their position, right, so to speak. So again, with the semicolons, you can take, say, a complex number and destructure it into its real and imaginary part. So if I don't know if you saw complex numbers very much, but if I create a complex number like z equals 2 plus 3m, that's a complex number. It's built into Julia. And z, I think I can probably dump it. Yeah. So z is a structure with a re and an im component. So it has like z dot rim, z dot im, and that's what's sort of inside z. Okay. And im itself is kind of like actually, I think it's a complex number as well, but it's a weird abstraction where it's a complex number, and they're using booleans to represent like a 1-bit integer. So 1-bit integer is obviously 0 or 1, and so it's like the smallest minimal shaped amount of data you might represent an imaginary number with, or a complex number with. Sorry. All right. And the other thing is you can combine these all together. So up here where that X is, it would have been perfectly valid for me to put this thing in brackets here, in there, and destructure it directly as they come into the function. And that's fine. So here's a little example. Here's F. It's expected to bring a pair, a tuple into it, a tuple with 2 elements into it. And it will sort of destructure them and then add them up. So my pair is this tuple with 4 and 5 in it. If I call F with my pair, I get 9. So it destructures it as they come in. That's cool. Another cool thing you can do with functions is you can pipe them. So if you remember the Unix stuff with the shell, and you could like pipe text from one program to another with, and in that case you just used a single one of those, right? Now in programming, often that character represents OR, like Boolean kind of OR, like logical OR. And so that's sort of taken in Julia. So we use this sort of combination of 2 characters to represent the piping. And so they take a value and then they call this thing on the right with that value. Okay. So if you take pi and 4 and pass it through cos and then arc cos, you'd expect to get sort of the same thing back, right? And then you pipe it into this whole thing as an anonymous function. So we pipe it into that function, which will take the input and multiply it by 4. Right? Then we get sort of pi back. Right? Sort of just a cutesy little thing. Now you can, because Julia supports functions as values, right? It's a higher order programming language. Functions can also be values and pass around to other functions. You can do higher order logic on functions. You can take 2 functions and compose them, for example. So function compositions, like when you if you have like f composed with g, right, then that's like f of g f x kind of thing. So yeah, it's a cute thing. Now, one thing, I don't know if Paul, I don't remember Paul showing you this or not. At the command here, you can do things like type /pi and then press the tab key and you get pi, right? Yes?
Is this circle operation the composition of functions in the opposite order than type in terms of application? So in the example,
yeah, I was just trying to remember that when I was explaining it. So so the circ operator is like this, right? Oops. Oh, I should have tested that. This terminal is a bit crappy. It doesn't actually have the fonts. So let's look at the thing. So F circle, that should be a circle. G is the same as F of G. Well, no, well, the pipes you do. Yes, it is actually. You're right, because you're doing G before the F. Yeah, exactly correct. Yeah, exactly. Yeah. Yep. Cool. Okay. This is probably another one of my favorite features of Julia is this dot syntax. Okay. So, and again, this is like a very small piece of syntax, but has a very important meaning. They kind of stole this idea a little bit from MATLAB. So MATLAB has this idea of matrix multiplications built into MATLAB. So you use the little times operator to multiply matrices. But sometimes what you want to do is multiply each element of the matrix by an element of the other matrix, right? And not think of it as a linear algebra kind of entity, but you just want to think of it as a collection of numbers and you want to like multiply or divide them. You don't have this ambiguity with addition and subtraction because it's sort of the same rule, whether you think of it as a linear algebra object or whether you think of it as a collection of numbers. But for multiplication and division, it's sort of a little bit different. So MATLAB had this dot star and dot backslash sort of operator, so you could multiply and divide things. And they kind of like took this idea and took it to the extreme. So you can, with operators, so let's make a little array, like array equals 1, 2, 3, right? And I can go like a, dot plus 10 or something. And we can add 10 to every element. Okay. What happens if I do this? What do you think will happen? All right, so that'll error out. So there's no linear algebra operation for adding like a vector and a real number, right? You can add two vectors and you can theoretically go into the vector and add 10 to each element, but that's not like a basis independent linear algebra operation, right? So that's a special thing with a special name, which is separate from adding in the linear algebra sense. What does the semicolon do there? I have a question from Mitun. I'm not sure. Sorry, I didn't see this earlier. Semicolon can mean two things. Often it can mean just don't show the output. So I could have 10 and it shows me 10, or I could do that and it shows me nothing. Okay, so it can silence the output. Again, that's another thing they stole from MATLAB. The other thing we saw the semicolon mean was it sort of introduces this idea, like we used it for the keyword arguments and for name tuples. So like a tuple might be like, 1, 2, 3. And like a name tuple, you might write like A1. And actually, in this case, it'll accept it either way. But I think the main place where it's different is for the empty one. It's kind of like you can have an empty tuple like that and an empty name tuple like that. Yeah. Yes, and that's the same with the destructuring with the complex number function. Is it was kind of like the opposite version of that. Instead of creating it, so it's destructuring it. All right. So yeah, here's an example. We create like a range of angles and we put each of those numbers through cos and we get this kind of these numbers out. And one thing that's really cool is you can go like, so I had my array A, right? So I can go A like dot times 2, and then like dot plus, 10, things like that. And even with brackets, you can put brackets around that either way, this way or the other way. And what Julia actually does something really very fancy. Have I got meta and skirt? Yeah. So what Julia does, and this is going to look really, really crazy. Sorry, just trying to get that back. It's going to look really, really crazy. But this is like taking away all the syntax sugar. It's actually doing a bunch of stuff here with this broadcaster thing. But basically materializes where it's doing all the real work. And so before materialize, it's just creating these sort of higher order sort of functions and things that represent this idea of taking an element, multiplying by 2 and adding 10 to it, okay? And then once it's constructed that kind of higher order function, it'll apply that to every element one at a time. And this is better than what you might do by default, which is like create a new array which contains this value and populate it. And then take that array and create a third array with the adding 10 to each element, right? And so that's requiring twice the amount of RAM and twice the number of like iterations through the arrays, then sort of doing it all in one thing. And there's this operator here, this macro, not operator, which takes an expression like that and just sticks dot everywhere it can go, so that you can kind of like do those kind of functions a little bit more easily. Just a cute little thing you can do. All right. So again, we just got a few more interesting items of syntax before we go into data types. Iteration. So you've seen if and else, for loops and while loops and things a little bit in Julia. One of the really, well, like a lot of languages, Julia has these continue and break keywords for the loop. So you can use break to exit a loop before it's meant to finish and things like that. But even more generally, you can use go to and label, okay? So that's within a function body, you can actually take over the control flow and create your own kind of like patterns and things. Now, this is a very old form of programming before structured programming sort of became ubiquitous. As everyone's computer programs in the 80s, say, and 70s, they would probably be like a large body of code and you'd use go to, and you'd go to line 110, right? And then you do some logic, and then you say, oh, if this number's a prime number, then you go to line 206. And you just have this huge reel of code and you just get jumping around like that. And it's sort of hard to reason about where it's going because it's a bit kind of crazy. But it also has ultimate flexibility, right? Underneath, like all this programming language is a computer. It's a bit like one of those von Neumann machines Paul mentioned. You know, it just has a reel of instructions that it goes off and you can point the head at like some other instruction, and that's what go to basically represents. So it's a bit more low level. So like you can almost think of a while loop, and this is like literally what it does. A while loop is kind of like it gets to the end, and while the condition's true, it goes to the top again. It gets to the end and then goes to the top, and that's what a while loop does. And a for loop's a bit like a while loop, but it adds this idea of iteration. So in Julia, you go for x and iterable. So some things are iterable, like we've seen arrays and things like this. So, you know, we had now array here, and we can go for x in the array, you know, print line x, and it'll do something for each element of the array, right? And so the way Julia does this, it uses this iterate method. It's sort of defined in the base standard library. And it's sort of like, it takes this for loop and basically turns it into this code here. So it starts to iterate it. It checks to see whether it's empty. If it's empty, it just sort of like skips this entire block of code, right? Because if you could do a for loop over an empty array, nothing happens. If it's not empty, you kind of get the value you're interested in, and plus this temporary state out. You do something with your value. That's this code block here is here. And then you iterate to the next element using the state. Now let's just have a look at this. Maybe I'm going to make a equals, I'm going to make this like this, just so we can sort of see what's going on. So we can go like iterate a, right? And we get the first element 1.0, and then we get the next index 2, the next index 2, right? And then to get the following thing, we put the 2 there. We get the second element, we get 3. To get the third part of the loop, we put the 3 there. We get that. And then eventually we do this and we get nothing, okay? So remember, just at the REPL, nothing prints as like this, it doesn't have any printing, right? So yeah. Cool. Hope you're done. And again, I don't really expect you to kind of like use this knowledge very deeply. I just want you to kind of be aware that it's possible to use the iterate function to like make your own data structure that you can iterate with a for loop. Right, so it's not just Julia doesn't just come with the data structures that it comes with, right? You can add new data structures and iterate through them and things like that, and index and all those other things. And B, you know, it's just something, just another syntax transformation. We're probably not going to focus a lot on errors and exceptions in the projects, but you will come across errors. Like you're often typing things at the REPL and you make a syntax mistake, something comes up with errors. So we'll talk a little bit about what the errors are, and a little bit how you might handle them in theory. But like, don't take this as like knowledge that like, you know, you have to study really hard and try and master or something, but just so you're kind of aware of it. So Julie has this error function, okay? It's actually shorthand for this throw function. What it does is it throws an error with this string message in it, okay? The throw function is kind of built into Julia. So you can throw anything, right? You can throw, but usually you throw some variety of error. And what that does is it basically stops executing the code, right? And it passes down this error until something catches that error. Or if it gets all the way to the top level of your program, it'll like quit the program completely, right? So that's what an error is. Now, when you're at the REPL will always catch every error and print it out for you and go back to the REPL. But by default, if like you had a script or something and it errored out, it would just stop running and take you back to the shell. You know, it just go away. And so here's a function which tries to invert a 2x2 matrix. If you're aware of how you might do this, you find the determinant of the matrix and then sort of like sort of take the transpose, but you're sort of taking the minus of the, maybe this would be easier on the whiteboard, of the off diagonal elements. And then you divide it by the determinant. And that's just a little trick for doing matrix inverse of a 2x2 matrix. Now, this function only works for 2x2 matrices. So to make the function sort of safe, we just double check this. And if it's, you know, if that's not happening, we tell the user that they screwed up. The other thing that can happen is a matrix can be singular. So, and a singular matrix can't be inverted. And the one way you can tell if a matrix singular is if the determinant is 0. Okay, so if the determinant's approximately 0, we throw an error, right? Now, because remember with floating point math, sometimes we subtract things that are pretty much equal, but they come off with this tiny little epsilon of error. All right, so we use the approximate sign there. And like you can see all the various different types of errors. Like here we try and call it with a 3x3 matrix. Function only works for 2x2 matrices. We try and call it with this matrix, which I don't know why it didn't work to, anyway, the way it's written is weird. But basically, if the matrix is 1, 1, 1, 1, it's singular, right? The determinant of that is 0. Is there a question?
Sorry, just a question about the equivalent sign. Yes.
This one, yes.
Yeah.
I believe Paul spoke about this, but so we can go like, you know, is 1.1 approximately equal to 1.0, right? That's false, right? But eventually, if I keep adding more zeros, we'll be like, oh, that's true. Okay. So what is the threshold it gives? Well, first thing is that symbol is syntax sugar for that, right? And we can look at its help. It has these two keyword parameters called atol and rtol. So that's relative tolerance and absolute tolerance. And the default for this function is apparently this, the relative tolerance of square root of epsilon. Okay, so what's eps? So if I go eps, oops, oh, there it is, sorry. That's like, kind of like, it's not quite, but it's kind of like, yeah. So if I go 1, that's eps, right? This is kind of like the next floating point number after 1. Okay, and so like by default, it kind of think about your algorithms and that if you're off by more than square root of eps, then there's probably something going wrong with the algorithm that's not just floating point error at the fringes, because in terms of the number of bits, you've gotten half the bits wrong at that point. Right, so that's a lot of numerical error. That seems a little excessive. And so like when you're checking if like your numerical algorithm is approximately equal to what it should, it's sort of just not a bad, just default to kind of like just use. But that's sort of how big the tolerance of that is a prox operator is by default. But if you use the functional form rather than the operator form, you can specify what tolerance you like, which can be useful sometimes when you're writing unit tests and things. Okay, here we're taking like some, we're getting some matrices, and we're using this assert macro, okay? So what assert will do is if this thing isn't true, if that's not true, it'll throw an error. So this way you can put in your code like before where we were checking things and throwing an error if something was wrong. This is like a shorthand way of doing that, right? It'll just throw an assertion error. You know, it's less coding for you as a programmer, but it's still checking everything's working. Okay. So it's a macro. So again, it literally will just expand into maybe we should just browse on. So it'll really expand into this kind of code. All right, so the macro just takes one bit of code, produces other code. That's the kind of code that it'll make. Okay. Maybe if I use the keyboard. This is sort of comical. Yeah, that doesn't help much better either. Try and catch. So I talked about catching errors before. This is how you catch errors. You put code that might error inside a try block, and then you try and catch the error. Sort of like this kind of thing, or this kind of thing. There's a third thing you can do here is called finally, which means whether it's through or not, make sure you run this code. Now, what is finally useful for? It's actually really useful for resource cleanup. So let's say you're opening files and that uses resources on your system, and you know you might want to close the file so the file can be deleted or whatever. You often use this pattern here, where you might try and like open a file. If you can open it successfully, you try and do all your file operations in here, and then finally close it. Now, what would happen without this try and finally is if something goes wrong in here, and when you're dealing with files, you know, you can run out of disk space. You might be trying to load the files RAM and run out of RAM. But there's a lot of things that can go wrong, even if you haven't really made programming errors, right? You just sort of have to assume when you're doing these kind of operations, your code might crash, and it's not your fault. It's not the user's fault, right? But you still have to deal with it. There's this finally thing, and that just means the file always gets closed. But you know, you might also try and delete the file and do other things in the finally block, right, to clean everything up. And so going back to our do notation before, like there's literally a definition of open like this in base in the standard library. And it's very common when dealing with files to use this kind of syntax here with the do. And then, so you go open file do, and then this is like a stream of bytes, sort of like Paul was talking about Unix pipes and like streams of bytes that go between the things. It's like one of those. And what that might actually throw an error. For example, you might try and read 128 bytes, but what if there's only 10 bytes of the file? Well, that's going to throw an error, right? So what will happen with this syntax, with the do and everything, is that actually that file will get closed after the error, right? It's not just the happy path where the resources get cleaned up, but also the sad path. Yep.
What is the point of finding? We just have to try and catch and.
Well, often what you would have is repeated code. So what is the point of finaling? Is often you would have the same code in the catch as you do after it.
Oh, okay.
And so what you'd find is programmers might make mistakes because the code might be a bit different in the two places, or they might forget to do them one and remember to do it in the other. And so it's just a little, again, it's more syntax sugar, right? It's just something there to help the programmer not make mistakes. Right? Error handling's notoriously tricky because most of the time when you test your code that's working, you're not testing the errors, right? You're testing the code working. You practice running that press it working, then you give it to someone else, and like guaranteed they'll figure out some way to break your program. If you haven't tested your error handling, then something's going to go more wrong than it should have. Scopes. Okay, so programming languages have this idea of scopes. Back in the dark days when compilers were first being designed, they had this concept called dynamic scope. So in Shell, for example, Shell, we have things like path. I don't know what's on. Oh, I'm not actually in a shell. I'm sorry. But we have these environment variables. Is that like this? Yeah. You have these environment variables in your shell, and when your shell program opens another shell program, it actually passes this dictionary of strings to strings into that other program. All right. And so on. So the variables sort of in scope at shell kind of get picked up by the functions that you're calling in shell, and that's sort of a dynamic scope. Lexical scope is more about the way it looks on the screen, the code looks, not the way the code executes. Not when you call a function, you give it all the arguments. In lexical scope, the function only receives the arguments that are listed, right? So this f, for example, doesn't accept any arguments. The only things f can access are the things outside of its scope, in its upper scopes. But if I call this function from another module or something, this function won't be able to see anything from that module, right? And so that's what lexical scope means. Lexical, it's just about like the shape of the code as the code is written, rather than like the path of execution. And so Julia actually has two types of scope, sort of a global scope and a local scope. So local scope is probably the one to me makes a lot of sense. You can't really go wrong with it. You know, a local scope, I can bind a variable x and like return 2x. But and what you could do when you have variables in different scopes is this variables, there's also a variable in global scope called x. And what this one's doing is actually creating a brand new variable on the inner scope, on the local scope of that function. So this isn't actually taking this x and changing its number, right? So as you can see, if we return 2x, we're getting 2. But the other thing to note here is this x hasn't changed, I don't think. Pretty sure it hasn't changed. And then there's like these local and global, there's things like this here that you can use to change the behavior. So I could have written global x here, and then that would have reassigned that variable in the global scope. Okay, so there are these extra keywords, global and local, that let you kind of tweak around with which variable and which scope you're talking about. The global scope in Julia, you can kind of think of as commands to give the compiler. They're like, compiler, can you please create this function f with 0 arguments with this function body? Right? That's what that function thing is doing at global scope, right? And for example, in global scope, you can like define function A and then function B, and then have A call B, even though B is defined after A, right? It'll sort of piece your program together after the fact. Whereas a local scope, you can't go y equals x plus 1 and then define x equals 2, right? You have to know x before you figure out y, because it's sort of like a sequence or procedure of things you have to do. Whereas at global scope, what you're doing is you're giving pieces of information to the Julia compiler that it uses when you try and run some code to sort of piece together your program. And so it behaves a little bit differently. Here's a little bit of a complicated example where we've got variables like s that are being used inside different for loops and things like that. There's a really strange behavior in Julia with for loops in global scope. Things that you wouldn't normally have to do inside a function, you might have to like add some extra globals and things inside the for loop, like at the REPL and things. And it's a little bit frustrating to get all this stuff right. So I actually don't really want to go through the details of what's going on here. I'd rather probably just offer a few pieces of advice, which is basically try to avoid using the global scope. Don't use a lot of global variables. When you have logic, computations you want to do or procedures you want to do, you can write them in a little script file, but like try and wrap them inside a function and then do that in there. And in that way, all your variables in that aren't going to get confused. You're not going to pollute the global namespace, smash your variables and things with other things. Okay. There's one nice little thing with scoping. In a for loop, the thing that you're iterating with normally goes away once the loop's finished, right? So we have f, right? It defines this variable I equals 0. We for I equals 1 to 3. And afterwards, I actually is 0, right? Because this I is a variable in a new scope, in the scope of the for loop, separate from that I. Okay, but if you want them to be one and the same, you don't use global, you don't use local, but you use outer. So there's another third keyword to help you with that one. Okay, so it's saying, oh, there's this variable I, it's in the outer scope. So this is like the inner scope, and that's like the outer scope from the point of view of this for loop. And you can kind of like, what will happen is as you assign things to it, they kind of remember. And that can be useful in one particular case, which is where somewhere in the middle of the loop you break. So let's say you're searching for a particular piece of data, right? You can write a for loop and then just break, and then that data is the one that you're looking for, all right? And so that can be a nice little pattern. But like I said, my advice mostly is use global variables as little as possible. Use distinct names for variables as much as possible. So rather than like shadowing variables with the same name, but like in a scope, that can be confusing because when the person comes to read your code, they're like, is that X or is that a different X? And so if you just called it X2, like there'd be the person wouldn't have to think. They'll just know that that's X2 and that one's X, and they're different things. And there's this nice kind of rule with programming is like, you often want to do things like write for I equals 1 to 3. But usually if that's for a little short for loop or something, but for the more lines of code a variable gets used for, the sort of the longer and more descriptive the name should be. You don't want to use I for something at global scope because you have no context for what that might mean, right? Yeah. So basically you want your programs to be simple and easy to read because you have to come back and fix your code. Other people might need to read your code. In the context of this course, you're going to do some pair work and you're going to get marked, right? So there's going to be several people that need to read and understand your code to get through the course. But yeah, that's just generally a life lesson. Okay, we're going to talk about types. Now it's 5:49. What we might do is we'll take a 5 to 10 minute break now, and I'll launch through types after the break. Is that all right? I'll just mute myself.
Did you see where?
This is 6 years silent.
Major changes to this animation. Which one is better? I'm definitely thinking that like it definitely feels the box to be like even I like yes, I think that I have the one it's more there's an interesting issue the feature is 5G and I'm like
Awfully sorry.
yeah, maybe that's maybe yes. I gave a question to that moment about when you merge these requests. Yes, you can correct it. Well, I was maybe 20 hours. So they do
I think it would be right. Especially at the end,
What's the yeah, it's a mini version and instructing versions. There's a version of confusing versions. That one, very carefully. I mean, it's just really one so they really as a
All right. Maybe we should get started again. So what I've sort of shown you before was probably just the surface of everything. So now we're going to delve into how the actual like data is represented inside Julia, and then more about functions. So types in the type system. Everything that's a value in Julia has a type. Okay. So if you can type the value out, then Julia knows the type of that thing. Okay. So there's lots of different types. For example, it's very numerical language. So the standard library has lots of different types of numbers. We have rationals. Did you see rationals at some point? So they're like actually representing fractions on the computer as like a pair of integers for the denominator and numerator. Complex numbers are built in, and there's lots of different things. But there's also strings, vectors. Vectors have a type parameter, right? So which is what is the type of the thing inside the vector. Or the array. There's an interesting mechanism in Julia called promotion. So promotion gets used in two places. One place is when adding, say, a real number and an integer, floating point number and an integer, Julia will first convert the integer to floating point and then add them as floating points. So that's promotion. And it applies the same set of promotion rules to the elements in an array by default. So here, when you write them out in a literal way, it's kind of like, okay, I'm just going to convert them all to floats because that's what the promotion rule says. Okay. Now, sometimes there's not actually a promotion rule. Like you can't turn a string into a number. So what it does, it gives up and does this thing called any. So any is a concrete type, any is an abstract type, and it represents the type of any potential value, right? So there's these things called tuples, which are instead of square brackets, they're written with curly brackets, and each of the elements in the tuple get their own kind of type. There's different types of like arrays and things. So here's an array, which is a unit range. And the reason I call it array is it behaves exactly like the other array. You can index and all that, but it's only taking up a little bit of RAM, like it has an integer representing the first value and an integer representing the last value, and then so it only needs like 16 bytes of RAM to represent that. There's matrices here. Now, the vector and matrix things, they're talking about these aliases. So there's actually one underlying type in Julia, the array, right? And it has a dimensionality as well as an element type. And matrix and vector are just, maybe I want to say syntax sugar again. They're just another way of talking about the same thing. Now types themselves, I said everything that has a value in Julia has a type. So even types have a type, and that's data type. Okay. One thing I don't really have here, but we have a bit later is, data type itself is a type, a value, and is also a type, sorry. And the type of data type is data type. So it's a bit circular. And there's these symbols. They're a little bit like strings, but they're special things for the compiler, and they can be a little bit faster to use than strings. So they tend to get used for like switches and controls and so on in your code. So concrete types, I mentioned the word concrete type. So concrete type means the type of a value. So we have types like any, and if I have a value like the number 2, the number 2 has type integer, right? Or int. Number 2 has type int. And that's a concrete type, which means Julia knows how many bytes that int is. It sort of knows where to store it on the computer and how to look it up and do things with it. But if you have an any, it's kind of like, well, Julia kind of needs to know more about that value before it could do anything with it, right? Because if it's anything, then like you can't do anything with it in a sense. Okay, so concrete type, if you have a value, it has a concrete type. There are also types which are sort of like supersets or unions of different concrete types, and they're abstract types. All right, so abstract types can have subtypes. It's sort of like a tree or a hierarchy. And at the leaves of that tree are the concrete types. So the most basic type in Julia is primitive type. So you can create your own if you want. Here are some things that are pretty much defined in the standard library of Julia, or in the compiler. And you can create them like this. So if you want to create your own float, 80 or something, you could using these kind of things. So you could have like a 10-byte floating point number, and you could describe how big the sort of exponent and the significand is, and define the operations for adding and subtracting on that floating point number if you wanted to. The only rule here is at the moment the number of bits has to be multiple 8, right? So in a very low-level languages like C, you can like define like the little bit layouts of all the different things. Julia is not quite that low level, but like they've sort of left open the possibility of doing that in the future. So by default, primitive types, they don't really have any methods associated with them. They're just bytes stored somewhere on the computer, on the stack, on the heap, or whatever. And you need to sort of define low-level kind of operations, like how to add 2 integers, and you have to sort of teach it how to do that. I think I showed last Tuesday, like, I showed you the code for how Julia adds integers, and it was like some other lower level code that are called. But the one thing you can do with primitive types is reinterpret them as another type. So you can take like this float 64 here and reinterpret it as a uint64, and you can kind of take a peek at what the bits are, right? And so like, I don't know if you remember Paul's course, but if you took the floating point number where all the bits were 0, that's actually equal to 0, right? And if we took, say, some other floating point number like pi, or like the nearest number to pi, and reinterpret that, we can see the bits of that, right? Primitive types in Julia are treated as immutable. Once you create a value, you don't edit the value. What you can do is you can create a new value. For example, when you add 1 to an integer, like semantically speaking, you don't like take that integer and mutate one of the bits in the integer and that's it, right? What you do is you like create a whole brand new integer somewhere else in memory, like in the theoretical memory model, and point your variable I over to this new value, and that old value still exists in a way. Now, what Julia can do, it can realize I'm never going to use that old value again, and so it actually might smush it in place. Okay, so it doesn't necessarily need to allocate more RAM, and it can only do that because it knows it's immutable. Right, so the optimizations like this sort of come out of guarantees. Guarantees like something is immutable means the compiler can make more assumptions and make better code. Okay. Structs. So that's how fundamentally that's where all your bits of data come from. They're all primitive types, right? Structs let you put together other structs and other primitive types and arrays and strings and things together into a larger data structure with named fields. So here is a oh, that's actually a mistake. That should be real. Here is a definition of the complex number in base, except for in base that doesn't say number where I've highlighted, it says real. So this sort of shows basically all the features there are of how you can define a struct. So it has fields. It can have an arbitrary number, 0 or more fields. They all have a name. They have to have a name of something. They can have a type. If you don't specify type, it just assumes any. Okay. It can have a type parameter, which you can then use to sort of refine the types down here. And it can have a super type. So the complex number is a type of number. It has a type parameter, which should be a subtype of real. We'll talk about real in a bit. And then once you know T, like T could be like float 64, then you have a real number, real component, which might be a float 64, and an imaginary component, which is a float 64. Okay. So that's basically all the features of struct right there. There's constructors too. We'll talk about constructors a little bit later, but that's basically everything. So, what's Julia doing here actually is it's actually adding a method to this complex object for the constructor. And what you can do optionally is override that method. It has a default one, which is the obvious one. So you get the type, and then you pass in a list of the values to put in the slots. And that's what the constructor is. So that's a pretty obvious way to make a constructor. There's no real other obvious way to do it, unless perhaps you might think keyword arguments or something. But yeah. So, for example, if I went to the REPL and just typed this in, the REPL would spit this out to me, right? That's fine. Like primitive type structs are immutable by default. You can't actually get into the struct and edit it. What you can do is create a brand new struct with new values. So when you add 1 to a complex number, you don't like take the real bit and add 1 to the real bit and leave the number where it was. What you do is you create a brand new complex number with new real and imaginary components. And you put it somewhere. And sometimes the compiler puts it straight on top of where it was. And sometimes it realizes that the imaginary component wasn't edited. So you can just leave it as it was and only update the real bit. But that's an optimization, right? Semantically, it's creating new things. Now, what we could do is actually create our own mutable structs. We might want to create a mutable complex number where you can actually edit it in place. And so this is very much like the old one. Sort of, again, that should be real. It should be some type of number, but whatever. And you could, for example, now perform this code without errors. You could create Z with a complex part, a real part of 2 and a complex part of 3. We could add 2 to the imaginary part, and you can see down here we have this number 5. Okay, so 3 plus 2 is 5. And what it's done is we haven't really created a new Z. This is the old Z, and it's been modified. So part of the reason the built-in complex type isn't like this is because it's faster to have it immutable. It can do more things. If the object can be edited and you stick your complex numbers in an array, it has to make sure that all those elements of the array obey these reference semantics. And what you end up doing is introducing more pointers and pointer chasing, and your RAM gets fragmented and all sorts of things. And so when you're doing numerics, the immutable struct is much faster than the mutable version. Okay. So we haven't really defined any methods on mutable complex yet, but we could, for example, define a show method. So there's this function in base. Remember, base is the standard library called show. There's this thing which is an IO. This is like standard out, something like that, right? Like it's what you're printing out to the terminal. And so you can print, the real bit and then like plus and then the imaginary bit and then im, and then it'll come out looking just like the ones in base. Okay, so this is how complex numbers are sort of, this is roughly how complex numbers are implemented in base, plus or minus, a bit of approximation. You can override the plus method here. So we're taking two of these complex mutable bits and creating a new one with real and imaginary components just added up. So it's pretty obvious. And then that just works out. So we've defined show, we've defined plus, and now we're kind of starting to do kind of arithmetic and making things pretty at the REPL and stuff. Now, if we wanted to, we could define multiplication and we could define division and all those other things. And we could also do some things like, let's say you want to add a real number and a complex number. Okay, so you could add a function, another thing that takes mutable complex and some other real number. And then you could takes a plus of a real number and a complex number. And then, well, that might be okay, that's fine, but what about other types of number and so on? And so you could like exhaustively write out with brute force a whole bunch of methods, right? But there's actually a better way to do this using sort of interfaces and things. And there's these tricks with promotion and so on with number and Julia, so that you just define this and you define a promotion rule and everything will just work out naturally. And the promotion rule you want is if you have a real number and a complex number, you just convert the real number to a complex with an imaginary component of 0 and then proceed. So you can create a lot of functionality with a few lines of code. That's sort of what you can do with those kind of interfaces. Data type. Okay, so Julia comes with a built-in struct or mutable struct called data type. It's pretty complex. It's got lots of things in it. But this is the thing which Julia uses to reason about types. Okay, so Julia has a compiler. Some of the compilers written in C, some of the compilers written in C++, and it has like a layout, like a struct in C, and the layout for the data type that it thinks in its head has this kind of layout, which is something you can write in C. The any, like the abstract types in this type, they're just basically pointers to other structs in C. Okay, you don't really have to understand any of this. I just want to show you that it's all there, right? And you can do things like, let's take the int64 type and ask, well, okay, so this is like, what is the type of all these things? Well, the type of all these things is data type, right? We can take the int64 type and ask its size, and we get 8, so it's 8 bytes long, right? What about complex float 64? Well, that's 2 float 64s put together in a struct, so that's going to take 16 bytes of RAM. Okay, so that's what that 16 is there. What are the names of the things in complex? Well, it's re and im, and these are those symbols. These are those strings that the compiler uses internally. What are the types of the two fields? Well, it's float 64 and float 64. Okay, so again, I don't need you to use any of this. I just want you to be aware that like underneath all of this is a sort of sensible sort of system. And you can kind of like, it's a bit self-referential in the way that like type of data type is a data type. But this is a Turing complete system, right? So in a Turing complete system, there are some weird consequences. You have something called the halting problem, which means there are programs which never end, but you can't prove they never end or whatever, and things like that. And if you have this kind of like logic or higher order logic, you kind of either need like a multi-level kind system or some kind of circular references like this to actually design that system and make it work. Was there a question over here, or was it?
Yeah, pretty much. How does Julia handle the recursive definition or the recursive typing, things like data type? But also when you look at while you chose the data type has Booleans underneath, but Booleans have type data type as well.
Yes, so they're good questions. So the questions are like, how does Julia actually handle internally all this like recursive things? Like there's data type, and the type of data type is data type, and inside data type is a Boolean, but you can't really define what a Boolean is until you know what a data type is, right? And so the answer is during when you build the compiler, it does this thing called bootstrapping, and it will like carefully lay out all those data structures in C, and it will actually like create, for example, data type with bool in it, right? And it'll just leave those bools pointers to like just to the null pointer, right? And then it'll go ahead and it'll create the bool object, and then it'll update the pointer inside that data type. So you could do this in Julia as well, because data type is a mutable struct. So you can actually go in and update those references after the fact. And so when you're at the REPL, don't edit the data types because you'll make Julia crash, right? But if you're a compiler programmer, it's something you might do when you're doing those things, yes.
And what then is the type data type? Because data type itself is constructed, but there's a type as well.
Yep. Sorry. This. Good. Very good. So type is an abstract type. Okay, so I'm going to talk about abstract types down a little bit. So the Julia has different types. It has essentially data type, which are your concrete types. Everything that's concrete is a data type, right? Essentially. Even like primitive types, structs, mutable structs, arrays, they're all data type. Things with type parameters, and you don't know the parameters yet, so like complex, that's another type called union all, and there's another one called union, and I'll talk about those a little bit later. Okay, but that's a really interesting question. Like I said, this is going well beyond the knowledge you need, but I just want you to kind of like feel comfortable in the environment and be able to like not be too confused when you're creating your own types. So Julia has some built-in types which behave a little bit differently to every other type. There's like 4 or 5 of them. And I'm just going to talk about the concrete ones. There's the abstract ones that I mentioned, union, union, type, and things like that. But here are the concrete ones. Arrays are a little bit different to things you can just build yourself in Julia. So they're Julia's type for storing arbitrary amounts of data. Okay. They have 2 type parameters, one for the element type T and one for the number of dimensions. There's these type aliases. You can create aliases whenever you want in Julia. They're just these constant definitions. Okay, so you can, if you have your own types, you can create your own type aliases. The vectors themselves are resizable arrays. So like a C++ standard vector, it's sort of both a linear algebra vector and a C++ standard vector, all in one little data structure. But the matrix and the other dimensions you can't resize. Okay, so like there's just these sort of interesting implementation details internals to Julia that sort of guide all this. But they're another fundamental building block in addition to struct and mutable struct and primitive type, right? And the other one is string. Another one is string, which is very much like an array of bytes, but it has a little bit other magic going on. For example, short strings might be optimized to be stored in a little data structure rather than in like an array and things like this. It should be mentioned, if you just have an arbitrary bunch of bytes like a file, you generally store the data in this data structure here, vector of bytes, vector of UNZ8s. Okay. Tuples, another built-in type. These are really important, especially when you think about multiple dispatch. So tuple is this thing you write with brackets. Tuple, you sort of generally index them to get the elements, but they actually have fields, and the fields are like the symbol 1 and the symbol 2 and the symbol 3, right? But this is how you get things. Or are they the integers? I can't remember. Anyway. But it has a strong relationship with how dispatch works in Julia. So when you write f of something, it sort of looks like to the right of f, that thing looks a lot like a tuple, and that's not an accident. They did that on purpose. And so like a lot of the rules around tuple are sort of one-to-one with like a lot of the rules about how dispatch works and functions and things. But tuple's the only type where you can have an arbitrary number of type parameters. It could be 0 type parameters, 1, 2, 3, 4. Every other type, when you define a struct or a mutable struct, you define exactly which type parameters it has. Name tuple is like a tuple, but you get to name the fields. I don't really want to talk much about it, but it's just another special one. Cool. So that's basically all the data types, all the concrete data types in Julia. There's really nothing more. Like that encapsulates everything you can do. So mutation is a thing which gets a little bit confusing. So we'll just go through about what mutation is in Julia, like what gets mutated, what doesn't get mutated, right? Because it can just be a little bit confusing what's going on sometimes. It's a little bit of interplay between like this the syntax and the scoping rules and like the actual mutation itself. Okay, so we'll just cover this again. So you can ask whether something is mutable or not with this it's mutable function, right? It's just a function that comes with Julia. 7 is a number, it's immutable. So is mutable is false. An array, you can always like take an array and add elements to array and edit elements in the array and things like that. So that's a mutable data structure. You can edit it. Okay, so what are sort of the rules around mutation, right? So when you pass a mutable variable to a function, the function can change the data contained within that data structure on the inside of it. Okay. But if you're just talking about like the variable names themselves, like the scoping rules apply to that. That has nothing to do with mutation, right? So if I have some function f of z and the body of that function is z equals 0, then that's not actually, that's just inside the scope of the function defining a variable called z, a new variable called z, right? It's just overriding that variable. It's not actually taking this integer, and it doesn't even matter that that integer is mutable or immutable. It's irrelevant whether that's mutable or immutable. This is just a rule. This is just what variables are. You know, you're just taking a variable inside this scope and assigning it another value. Yeah. However, there's syntax like this, and this is why it's confusing, is because we use the same symbol to mutate something inside a data structure as we do for assign or bind a value to a variable, right? It's the same kind of equal sign here. And it's also the same equal size we use for this function form, which is creating a function definition for it. So it's actually kind of really overloaded kind of equal sign. So like, for example, we take this first f of integer and we pass in an integer. We, you know, before and after, we call the function, like x hasn't changed. Just because this thing's rebinded the variable of the same name, that only affects this scope. It doesn't affect the x in this scope, right? That's just scope rules. But if you have like a data structure, like an array or something in it, which is mutable, and we're editing the inside, then if you have a look down the bottom of the screen, the f has actually edited x. X has come after the function, x is has different values inside, right? So that's what we mean by mutation, right? So it's got to do with effects that you can observe outside of the function, right? These are all about what we call side effects in programming. So a pure functional program is like mathematics, right? When you call a function in mathematics, f of x or sine of x or something, you're not editing data structures and changing things elsewhere, right? It's only like a local computation. But mutation's all about like taking something that's on your computer and editing it, and other things can observe it. And everything interesting you do on a computer, like draw pixels on the screen, they're all side effects, right? Like you add the integers and multiply the floating point numbers so that you can print something out on your screen, and that has the side effect of making you think something, which is nothing to do with the computer at all, right? Okay, so the rule is you can mutate inside mutable values. That's the rule, right? But when you use equals for variables, you're just rebinding the variable. You're not editing or mutating or changing memory anywhere or anything like that. Okay. That's the rule. Now, when you have data structures that are mutable, that's mutable. You can you might want to copy them, for example. So the first one's just talking about variables, not really mutability or mutability. But here, let's have this variable A, which is equal to this array. Okay. And then we say B is the same as that array. And we edit B. Well, B and A are the same, are the reference to the same data structure. So A is actually changed. You see, A started as this, and now it's actually changed, right? So this is what we mean by side effects. Like this thing not only affects B, which you can see, but it's also affected A and so on. But to avoid this kind of problem, you might want to take a copy of A so that B is actually now its own data structure independent of A. And so when you edit it, you have A is what it used to be. Okay. So when you're using copy in Julia, it's often of this sort of defensive copy form. You're like trying to create something new so that the old things are destroyed. Yeah. Shallow copy. Okay, so the copy operation is only one layer deep. It sort of iterates through that array and makes copies of all those things. But if it's a deeply nested structure, like an array of arrays, it's actually only copying, let's say, it's only copying the pointer or the reference to that data structure and putting it into B. So it's got the same pointer or reference to this inner array, and then you edit that inner array, and then that actually has affected A. Okay, so there's this function called deep copy. This is sort of built into Julia. It will automatically go recurse into all the structs and arrays and everything, and copy everything and make a brand new. It's sort of guaranteed by the compiler that like that's a brand new piece of RAM. That if you edit anything that pre-existed, you can't affect that value. It's its own sort of safely copied value. The only caveat is deep copy is very slow compared to copy. Yes.
So the difference between doing B equals copy of A or just doing B equals A?
Yeah. All right. So yes, this is probably that's these two. So if we go B equals A, what we're just saying is B and A are variables that point to the same data structure, right? After that line of code. So if you edit that data structure, it affects both B and A. Right? Now there's this function called copy, and copy is a function. What it does is it creates a new array and it pushes all the data into it, all the old data, right? So it allocates fresh RAM, it iterates through the other array and like copies it into the RAM. And so now B is pointing to this fresh piece of RAM that didn't exist before, and A is still pointing to its existing piece of RAM. And so if you edit one, it doesn't affect the other one. Right? And this goes both ways, right? Like A and B are sort of decoupled from each other because like I could have edited A and then B would have changed, for example. So it's sort of like it's both directions. The copy keeps you safe in both directions. Does that help? Is that a little bit better? Yeah. It's a bit mind-bending at first, but like once you get used to it, it's not so bad. Cool. Abstract type. So we have not quite half an hour, 20 minutes left. So they're every single, I think I've gone through basically every concrete data type in Julia. So that's probably a good foundation. Now there's also these abstract types, and we use them a lot when we're defining methods for functions. So it's sort of worth knowing a little bit about what they are and how to use them. And we're even going to talk about how do we design types, abstract types and concrete types to actually make a program, a useful program, okay? That's where we're going with all of this. So all these types here are just in service of you writing programs that make sense and do useful things. And the abstract types help us write programs which are generic and reusable. So like there's an abstract type of number, for example, and we can write generic functions that work for all types of numbers, right? Like might be add one to a number, right? And I can do that to a complex number or a rational number or a floating point number or an integer. I can always increment them by one. And so that means I could use that incrementing function in other code, which works for all numbers, right? And therefore I get to put together my code, generic code with generic code, and build a program out of Lego bricks essentially. And it's actually a collection of programs that works on floating points, it works on integers, it works on complex numbers and different things, right? So I can write one lot of code and it's sort of equivalent to maybe hundreds of different possible programs in a sense. And that's where we're really trying to get to here. And that's the reason why Julia's pretty good for doing mathematical style programming. So, all right, Julia has a hierarchy of types, like a tree, right? So you have like at the top of the tree is this type called any, right? That's at the top of the tree. And this is probably confusing when you think about trees growing out of the ground, but like the tree's going downwards. And off that branch, different types and abstract types, which might be subtypes. And then you might have like number and you can go both directions, right? So let's look at this code here. We start with the number 2.3. What is its type? Well, its type is float 64. What's the super type of float 64? Well, it's abstract float. So abstract floats include float 32, float 16, float 128, right? They have functions on them like add and multiply, but you can also ask them what's their EPS. Remember we saw EPS before? You can ask them how many bits of exponent and significand they have and things like that. And then there's the super type of abstract float, which is real. So real numbers, you would expect they would be ordered, for example. You can always tell if one real number is bigger or smaller than another real number. And they're sort of closed under division, things like that. The super type of real number is number. So number includes things like integer, which might not be closed under division and stuff, right? And the super type of number is any. And any is at the top of tree. And we've got yet another one of these like little circular relationships. The super type of any is any. Yeah. Cool. There's a function called isa, right? 2.3 is a number. True. 2.3 is a string. False. Okay. It's both a function and an operator. So like plus, you could write it either as a function or as an operator. Isa is just a function which talks about is the type of the left-hand side a subtype of the right-hand side. That's also an equivalent thing, right? So that's sort of saying, is float 64 a subtype of number? That's true. Is string a subtype of number? That's false. Okay, so that's where this true and false came from. It's from these type relationships, okay? So this is sort of like less than or equals sort of sign, but with a colon. And like the double colon in Julia is sort of like equals equals, but with colons, right? And that's kind of like a cute little bit of syntax they came up with to talk about types. It's sort of like an ordering or a partial order of types. Okay, we can ask whether a given type's concrete or abstract. These are just little functions that come with Julia. Float 64 is not abstract, it is concrete, blah, blah, blah. The real type is abstract, it's not concrete. Fair enough, not too complicated. Complex is an interesting one. So complex normally takes a type parameter. So when you know the type parameter is float 64, then you know it has two 8-byte float 64 numbers inside it, and it's 16 bytes big. And when the compiler is dealing with the program, it knows, okay, I need to put 16 bytes here in memory to store this thing, and so on. If I want to send that across the network connection to some other computer, I can send 16 bytes, right? And that's a concrete value. Yes?
When you say 16 bytes, is there overhead associated with the data type as well?
Only, okay, that's a good question. So when the fields are all the same length, like that, and they're all powers of 2, there's no problems. You just add them up. Now there's rules which were invented by C, it's got the System V ABI, which sort of determines like whether there should be gaps. So let's say you had a Boolean and then a float 64 number in your struct. It would actually write a byte and then leave 7 bytes empty and then write 8 bytes. And so even though that's only 9 bytes data, it would actually store it in 16 bytes and things like that. And so there's rules that come from the days of C that were invented by the people who created Unix, which we all tend to follow for like how these data structures are laid out. And the reason we follow these rules is Julia is a good language for interoperating with C or with Fortran or with Python or with JavaScript or with R or whatever. And they all interoperate with each other because they all agree on the number of bytes in these structs and stuff. Does that help answer your question a little bit? Yeah. But yeah, in the case where it's just 8 plus 8, it's a nice simple layout and they're just squashed next to each other. Now, where I was going with that is if that was a complex of float 32, it'd only be 8 bytes. If it was a complex of something else, there might be pointers involved and different things, right? So complex, without knowing what the type in it, it's not a concrete type, right? The compiler doesn't yet know how to deal with that data because it could be laid out however. It wouldn't know how to get the infield because it wouldn't know how many bytes in the data structure to offset to look for it and things. All right, so that's not a concrete type. But once I provide that type parameter by float64, that is a concrete type. That is something where we know everything about the layout of that type in RAM. Okay, that makes it concrete. We can then use it. Cool. So here's a little program. Now it's a cute little program. I don't really want to run through exactly what it's doing, but this is a little loop and it goes through all the children of this thing. So you start with a type, and if it's concrete, you print out the type. If it's not concrete, you look for its children, its subtypes. So we had supertype before. There's also a subtypes function. So we're going down the tree, not up the tree this time. And then we go through all the children and we write them out. And I've got this little cute stuff going on with Unicode to make it look pretty. And I'll show you what that looks like. So we start with number, remember? Now, if I did this with any, it would take up pages and pages and pages because it would print out every single type in Julia. And we don't have time for that. But hopefully if the browser isn't slow ass, which it is, we can look at all this at once. Hurrah. Okay, so numbers at the top of this tree. And there are things like complex dual numbers and reals underneath that. And real numbers are broken into abstract floats, abstract irrationals, integers, rational. Why is it abstract irrational and rational? Abstract irrational, sorry. That's things like pi. So there's special number types for pi and Julia and stuff. It's kind of cute. And we've loaded the stats package, so we've got a few extra things in there to do with statistics. And so before we were looking at float64, and we saw it was an abstract float, which was a real, which is a number. But here we can actually see everything laid out and how they relate to each other, and which ones have type parameters and which ones are, don't, and things like that. Okay. Again, that's just a cute little thing for visualizing it. Right. So I showed you how to define all the rest of your types, but like the abstract types, they're not too hard. It's a little bit like primitive type, except you don't need to specify how many bytes it takes. So it's abstract type and then the name, right? And if you don't specify a thing on the right-hand side here, then it just it just attaches it below any, right? Directly to any. So I could write number less than, colon any, and it would be identical. Wouldn't make a difference. But here we can like make our entire tree of different types and attach concrete types to the leaves, right? And we can go in and we'll probably go through a full-blown example next Monday on this. We've just got an example a bit below, and you'll probably define a few of your own types and things for your project so that you can create things and use things and pull verticals, start leading you down that path. And we'll get back to that also again when I come back with Unit 6. So another abstract type in Julia is the union type. This one's not too complicated. Let's say a variable could either be an integer or float64. So we can take the union of those two things, right? It's like set theory. It's like the union of two sets is this thing, right? So in Julia, it really only has 3 types of abstract types. There's these abstract type keyword things we have. We got these type parameters. They have something to do with something called union all. So it's like the union of all complex numbers where T is a real number, and that's a union all type. That's got to do with type parameters. And then there's these unions. And just to sort of complete sort of the mathematical computer science thing of the type system. So union is another thing. It's an abstract type though. It accepts an arbitrary number of things, 0 or more. So if there's one thing, union of something is just itself, right? That's like a rule, an axiom, a piece of algebra we can apply. And then things like this. There's all these type relationships in Julia that the compiler applies internally to simplify things and to figure things out. Okay, but there's this type. This type is beautiful. What is the union? What is that? Can anyone understand or explain to me what that might be? Yeah, it's kind of like the empty set. That's right. So unions like set unions, right? So if you start with an empty set, so empty sets, that means, that implies that there's no value of type union, right? And so the compiler uses this internally to represent variables or types or whatever that are impossible. So bits of code you could never reach, it's guaranteed you'll throw an error before you get to that line of code. And so it'll sort of say, okay, well, that variable's this thing because you'll never get there. It's impossible. Just like we sort of said that Annie was at the top of the tree, we kind of say that union is at the bottom of the tree. And they're kind of opposites. And like there's a bit of algebra, kind of category 3 style algebra stuff going on with this. That's really interesting from a computer science point of view, but that's not the purpose of this course. All right, okay. Actually, we will get into this little thing. So are there any questions before we? Yeah. So that's like the entire type system, right? Like I've shown you almost all the syntax, all the types. So hopefully when you see something, it's not going to be like, oh, I don't know what that means, but you know, I don't expect you to remember all of it. It's a huge whirlwind tour, just a massive brain dump on you guys. So I don't want anyone to feel bad that they didn't keep up with a certain aspect or something. We're not directly examining this. We're just trying to give you the foundation for doing projects 1, 2, and 3, right? All right, so I sort of said this before, you know, when you're doing your own projects, when you're doing serious programming, you're likely to need to define your own types, right? And because with your own types, you'll be able to define your own methods and logic on those types. So that's really the beauty, that's the reason, right? Sometimes you have data, you need to store it somehow. And sometimes you could store the data 1,000 different ways, but you need to define a type so you can define the operations on it. So let's take like a person. So in an object-oriented language, you might create a class. Like in Python, you might create a class with a person with fields in it. In Julia, it's a struct, and the functions are separate from the struct. Okay. So we've seen this before. We can create a person struct, right? And that struct comes with a constructor. So that's a function on person, which takes 3 arguments, which are the field values. Okay. So here's a person. Miriam is 179 centimeters tall and 78 kilograms. And so on. That's all fine. We can see we didn't use mutable struct, so it's not mutable. And so if we try and update the field, we get false. So we get an error. Sorry. So if we wanted to be able to let people gain weight, for example, then we would have to make that mutable, right? And that would sort of fundamentally change the assumptions you can make about the data, whether it's changing behind the scenes or not, affect the way you program runs. So we could just have created mutable person, and then it would have been perfectly legitimate to update Miriam's weight like that. That would be fine. Okay. Now, in Julia, you can't normally redefine functions and structs and primitive types and things. Like there's some things the compiler sort of treats as kind of constant and just assume aren't changing. And if you want to kind of like change your program in some fundamental way, like remove a struct, you normally just have to like exit Julia and start Julia again, right? So there's this package called revise, which will kind of like keep everything up to date with your files automatically without having to quit and reload and things like that. And so if you're doing any serious programming, it's a good one to install. You can use Jupyter notebooks. That's pretty sensible. It does sensible things. Or Pluto. Pluto's another thing like Jupyter. And VS Code. VS Code will help, but VS Code plugins will help you kind of like rerun your code and stuff as well. But this is just one thing you're going to come across because you're going to be doing project 1 and 2. And I guarantee you're going to create data structures. You're going to want to change them because there's going to be something wrong with them. And you're going to see this thing. Okay, so I just wanted to warn you. It's just Julia being finicky. It is theoretically fixable. It's just an implementation detail in Julia. So they've fixed a problem where you can redefine function methods in Julia, and that's fine. They haven't gone all the way and let you redefine const and redefine struct and primitive type and things yet, but maybe one day. It's interesting when you get into programming because everything's a work in progress. Even C and C++ are languages which are changing. We're nearly at the end of the session. So what I've got here is a little bit of a type hierarchy that we can create of our own types, not just people, not just humans, but like all sorts of animals. And so what we're going to do come next Monday is we'll just run through this. Like, how do we create our own system of objects? And now that we have all these objects, how do we define functions and methods on them? And we'll talk about something called interfaces, which are kind of like functions which you can use on generic or abstract types. And other people can assemble programs using sort of abstract types and abstract and generic functions. And they can go away and be very productive doing their own work. And Julia will put together the program for them and make it run very fast. Okay, so this is how you get the programming is fast for the user and it's also fast for the machine. That's sort of the thing that we want to get out of Julia. So that'll be my focus the next lesson is like, how do you, now that I've shown you a whole bunch of stuff, how do you take advantage of it? Like how do you use it? How do you get that power? And then again, projects 1, 2, and 3, you're starting to apply some of these things to solve three very different and very interesting kind of problems. Anyway, thank you. If there are any questions, let me know. Otherwise, I'll see you Monday because you have the quiz tomorrow to remind you.
Mine's relative to this.
I have a question.
First one.
Yeah.
Can we? I don't know what you call like be a subtype and multiple types.
No, yeah. So we don't have multiple. You don't have multiple parents, you know. Yeah. So the type tree is a tree. So in so in C++, they call it multiple inheritance, right? You can inherit the things. Sometimes you want things that sort of are a bit of this and a bit of that, and this is where the interface and the traits help a lot. Yeah. Yeah.
And then the other question was, what's the parameterized types and the types?
Okay. All right. That's a really good question. Okay. So if you want to come around, it's a fantastic question. So what's the difference between a parameterized and abstract type? So when you have like this, the abstract types, you know, you have a super type and you have like a finite number of subtypes.
Yep.
There's animal and there's exactly 2 subtypes.
Okay. Yep.
Right, and that's sort of a fixed. Now you can always add more.
Yep.
Later, but that's at any point in time there's the exact number, right? But if I take complex, right?
Oh, I could have a complex of a complex. Oh no, that's not.
Well, there's more or less an infinite number of things I could put inside here.
Don't they all have to be a type?
Sure, but
And then
you could theoretically have.
Real is an abstract type, so therefore it's fine. I guess.
Yeah, but it can.
complex of
But
a,
you-
like,
yeah, you could have
complex,
stuff.
so let's say holder of any, and then in
Yeah.
any, we can put a holder of a holder of a.
So one thing, for example, you can create a tuple of uninates.
Yep.
This is something. This is just a thought experiment.
Yeah.
Right. So bytes.
Yep.
And the tuple can be arbitrary long.
Yep.
And you can make that a type parameter. And so you could actually have like a complex number with an arbitrary number of bytes.
Yeah.
And then there'd actually be theoretically an infinite number of
Yeah, no,
different
Yep.
things. So it is actually
Yeah.
and so there's this union thing as I mentioned, right? There's this thing called unional.
Yep.
And when I look at complex is a unional, and it has a couple of things in it. It has like a body, which is that thing.
Yep.
And a variable, which is t, right? And then when I do complex of like whatever, 64, it's actually doing things to those two data structures to figure out what that thing becomes.
Okay.
Yeah. Yeah. So that's sort of the difference. Yeah.
I have a question on mobile.
Yes. The prime number thing. No.
Yes.
Yes.
Yeah.
Um,
Well, I mentioned you got it under a second.
yeah, I actually had a question here on the chat.
Oh, really?
What I can do actually is pull that up and bring it in next week.
Okay.
Would that be okay?
Can I guess?
You can go. Yeah, sure. By the way, like I haven't done this for a year, so
Oh,
it's sort of out of my memory.
do you make direct calls to the scene?
No.
So it's just pure Julia.
Yes. So the nice thing about Julia is even if you do make direct calls to C and you put them inside functions inside other functions, the compiler will actually like inline all that and bring all that code together. So it's sort of like it does it for you.
It's down to 1.2 seconds when I typically look down and change.
I don't know. It also depends on your computer, right?
Yeah.
Yeah.
Oh, yeah. He had a good algorithm to begin with, and then it's just doing inbounds and the profile.
Inbounds. Okay, so inbounds is really important. So that's something I do a lot of.
8 seconds beforehand, and we got it down to less than 1
Yeah.
second in the one check.
Did anyone make a multi-threaded program?
I tried at one stage, but then I was like,
Yeah.
I just found the question.
So if I'm just going by memory, I think it was something around 1 second, and then I multi-threaded it, but then it was a bit less. So maybe 1.2 is very similar to what I have, but I can find it, and show you next Monday. It's several of you are interested, so that's good to see.
Yeah.
That's cool.
Yeah, that was pretty much it. I didn't have a question beyond that.
No, that's all right. That's all right.
Okay.
All
Thank
right.
you.
Hope you guys are having fun.
Yeah, this course is great.
Awesome. Thank you.
Oh,